Okay, so basically my talk, like Luke says, is going to be just a brief overview of what eigenvalues and eigenvectors really are. So most people are probably familiar with these. I know there are some sixth form students in the audience who have probably never heard of the concept, so don't worry, I'll go slowly, and it's sort of a linear algebra refresher as well. So first of all, what is a vector? So formally speaking, a vector is an element of a vector space, but to ground it a bit concretely, we'll think of vectors in two ways. So we'll think of vectors as coordinates, and we'll think of vectors as arrows pointing in space. So that's what I want you to imagine when I say vectors. In 2 dimensions, we have the basis, which is I and j. These are the vectors that make up everything else, and they're sort of the foundation from which we will begin and build everything. From I and j, you can get everything. So if you want, for example, 2, 1, you just move 2 in the I direction and 1 in the j direction. Like I said, by scaling and adding, you can reach any vector in the 2D plane. And for example, 8 minus 2, you can easily find it. It's 8i minus 2j. And more general for x and y. So we have our foundation. Now let's move on to matrices. What is a matrix? So it's a rectangular array of real numbers arranged in m rows and n columns. So like a 2 by 2 matrix looks like this. And how does it act with vectors? So you probably know the process: 1 with 4, 3 with minus 2, you know, like the rote technique of it all, which in general is this equation. But so what happens to the basis vectors when you multiply by a matrix? If you multiply it by I, by 1, 0, you'll always get the first column of a matrix. So you get AC. Similarly, if you multiply it by the j, so 0, 1, you'll get BD again. So yeah, if you want the columns of a vector, you multiply it by the I or you multiply it by the j. Now I sort of want to bring you into this geometric world of matrices. So what will happen? So first of all, we have the I and j, and from the I and j, we can get all of the points on the grid, infinitely many points on the 2D plane. What will happen to the I and the j? So the I will go to the first column, which is 2, 0, and the j will go to the second column, which is 1, 1. So it looks like that. But then what happens to the rest of the points? So the rest of the points move along with the basis vectors. So in the way the plane is transformed, like that. So you have these new grids. So let me do an example. If you have, for example, 1, 3, so you have 1 in the I direction, 3 in the j direction, you'll get this vector right here. So that's 1, 3. And when mapped using this matrix, then, so the I and j move, and where does the vector move? So the vector moves as if these were the basis vectors. So if it's 1, 3, you go 1, then you go 3, 1, 2, 3. So the image of this vector goes here, right? Let's sort of do another example. If you have the vector 1 minus 1, which is 1 with the I direction and minus 1 with the j direction. So that would be this one. After the transformation, so after the plane is transformed, its image is 1 minus 1. So coincidentally, it ended up at the same place. Obviously not coincidentally, because I know the numbers before I choose them, right? So does this happen always? How do vectors behave when transformed under a matrix? So for this, I found a really cool animation. I have to change the screen share. So this is Mathematica, and we have the matrix 2 minus 1, 1 minus 1. So as you can see, the I vector goes to 2 minus 1, and the J vector goes to 1 minus 1. So, pick any vector. So 2, 0 goes way beyond there. The vector 1 minus 1 goes somewhere else. But does this always happen? Can we find a vector that stays on the same default line? So if you sort of fiddle around with it a bit here, see, if you use that vector, then it stays on the same line, and the area of these two vectors is 0. And if we can find another one, like this one would be the same vector as that one, because it's the same line, default. So we have to find a different one. And I think that's it. So those are the eigenvectors. These vectors are sort of scaled up or down, and in this case, this one is scaled by a negative number because it's flipped, and this one is scaled by a positive number because it's stretched out a bit. So let's see another example. So for the matrix minus 1, 1, 1, 1, you have this eigenvector and this one. So same here, it's scaled by a negative number, a positive number. The scale is the eigenvalue, but we'll talk more about that later. What about this vector? So then this one. So this one is actually a rotation. So it's a rotation by 90 degrees. If you see, every vector will be rotated 90 degrees. So you can see that sort of by definition, it doesn't have any eigenvectors, right? Because you can't find one, no matter what you do. You can't find one that stays on the same line. And for example, this one, you have an eigenvector here, but there aren't any more. This is the same one, this one, and there's no other eigenvectors. So what gives, tipo? So sort of what just happened? All right, so the eigenvectors of a matrix are non-zero vectors because obviously 0 will stay the same no matter what matrix you multiply it by, and they keep their direction after being multiplied by m. They're only scaled by some scalar, lambda. So this equation shows it perfectly. Lambda is the eigenvalue of the matrix. So the eigenvalues of the matrix M are the values for lambda for which this equation holds. So how about some numeric examples? As you can see here, quite obviously, I is the eigenvector of this because it will be the column, which is just a scaled up version of I. Also, a bit less obvious, you have 1 minus 1 is the eigenvector with value 2. So if you calculate it, you'll see why. See? So when does this happen? How do we know it has eigenvalues? So we have this nice equation here, and we do some maths magic. We add in the identity matrix. So this has to be like of order n because of the dimension. Because the identity matrix, the one with the columns that are all 1 and the rest are 0, the diagonal, it doesn't do anything to the vector. It keeps it the way it is. So you sort of rearrange that and you get this equation. So it only has solutions if this determinant is 0, because you can think of this like a row of equations. So how many eigenvalues does a matrix have? Well, if you solve for the determinant, as I think you're very used to doing, like mechanically, you always get this polynomial. So the polynomial is always of degree n, where n is the dimension, right? So we have a 2x2 matrix. We'll always have a polynomial of degree 2. So like the most you'll get is lambda squared, which means that it only has up to 2 solutions, right? So similarly, n by n matrix will have at most n eigenvalues. So, okay, cool concept, but why are we doing this? It has various applications, so image processing, search engines, but this isn't my job, right? So you'll see in the next talks how such a simple concept can really emerge everywhere you look, which is truly the beauty of mathematics. I have something so simple that appears everywhere and is used in everything. That's it. So, any questions? I hope that was clear.
In the absence of questions, I'd like to say that was really great, Adriana. So even as a fourth year to theory and having not had an introduction to eigenvectors and eigenvalues in a couple of years, it was really nice. You had really great animations, especially the Mathematica one. It was really nice to see. And thank you for putting in that effort to make these slides. I know these were your first LaTeX slides, right? With using Beamer. So they were really pretty. So props and from my end.
Thank you.
Well done. That was
a lot of time. Thanks.
Well done. Very, very clear.
Thank you.
Okay, so thanks again, Adriana, for that. So if anyone has any questions for Adriana. Okay, maybe I have a question. Okay, so that that graphic you did in Mathematica, where you get that like a parallelogram, right? So I don't know, like I'm trying to think about like what does the area of that parallelogram mean anything of the, like when you have the image of the vector and the vector itself, what does the area mean?
I mean, the point of that animation, like I didn't make it myself, though. I'll write where I got it because I'll look it up, which I forgot the name. The point of it is that it's like a game where you try to make the area 0, so you find the eigenvector, because it's always 0 if they're the same, you know, like they're the same direction. So that's the point.
Did you get something like proportionality to the modulus of the cross product or something?
Yeah, I think it's related to the determinant.
Yes. I'm going to talk about that.
Okay, so Prof. Shri has going to say this later on.
Yes, I'm going to talk about that. In fact,
okay, that's good. So we won't spoil it then, so we'll wait for that. Yes. Okay, so
I was alarmed when I was watching because she took most of what I'm going to say. But
okay. So well, in the meantime, then, so that we don't spoil any more of Prof. Shri's talk, let's go to Prof. Shrirep's talk now. Fidek Andre.